In the previous class, we have seen that a conventional source of light, conventional source of light is incapable of pumping a gas laser. We also have learned what is the reason for this. Today, let me once again very briefly summarize what we learned in the previous class. This is the reason for this essentially is because of the fact that a conventional source of light, for example, flash or an arc lamp, emits light all around. That is because the light originates as the result of spontaneous emission. So it travels in every possible direction from this source. Now, only a small fraction of this light will be intercepted by the lasing medium, which in this case is a gaseous gas. Now, you know that the atoms or molecules which make up this gas, they have considerable empty space between them. And therefore, most of these photons will pass through this medium unabsorbed. It will not interact with an atom or molecule. There are a lot of empty spaces. However, there is another important reason. This is because the emission or a conventional source of light emits photons that have widely varying frequencies or wavelengths. That means the emission width of the source is pretty large. Say, this is the frequency. So the emission width, as you can see, we call it delta nu, which is quite large. And in contrast, the absorption rate of this gas which has to be pumped, its absorption rate often can be much smaller than this. Say, its absorption rate is delta nu. And the emission rate of the source is usually much more than the absorption rate of the gas which has to be pumped. And therefore, most of the photons anyway escape without being absorbed. But even the photon that probably is interacting with an atom or a molecule, it may or may not be absorbed. Why? Because if this photon's frequency, suppose this is the frequency, this photon has a frequency which lies outside this absorption feature, and therefore this photon cannot be absorbed by this molecule. Only if this photon frequency happen to lie within the absorption feature of this gas will it be absorbed. Therefore, these two are the primary reasons. First, it emits light all possible direction. Therefore, only a small fraction of the light will be intercepted by it. On top of that, the atoms or molecules which make up the gas has lot of empty space. Then, therefore, most of these photons, the number of them are already less, because only small number of photons will be intercepted, and even most of them will pass through the medium unabsorbed. Even if some photon interacts with the atom or molecule, it may or may not be absorbed, because if its frequency lies outside the absorption feature, absorption rate of the gas to be pumped, then it will not be absorbed. Only if this photon's frequency lie within the absorption profile of the gas will it be absorbed. Now, in contrast, laser emits. If you have laser, it gives a directed beam, unlike the con. And you now know the reason why so. Therefore, if you use this beam to pump this medium, so I better draw it here. So if you use this directed beam of, which gives a directed beam of light, the gaseous medium that would be pumped would intersect it pretty well. The beam can travel through the entire length of the gaseous medium. Therefore, there is chance that it will interact. Photons emitted by this laser will interact in a much better way with the atoms or molecules of this gaseous medium, and there is a possibility of that. And the possibility is pretty high because, as you also know, the emission width of the laser is much less, much narrower. This is the emission of width of the laser. It is much narrower compared to the large emission width of the conventional source. And if you can choose your wavelength of the laser appropriately, that is matching with the absorption wavelength, line center of the absorption of this gaseous medium to be pumped. That means if you can choose your laser wavelength appropriately, then there will be good overlap with the photons emitted by this laser and the absorption of this gaseous medium, and therefore there can be quite significant absorption. Therefore, both these disadvantages of a conventional source of light can be eliminated in case of if you use instead a laser as a pump source. But there is still challenges that have to be overcome before a laser can be made to pump such a gaseous medium. Let us see as to why. You see, this is our gaseous medium that has to be pumped. So, if you have to make a laser, you have created population inversion after pumping, but if you have to laser, then it has to have its own cavity. That means it has to be placed between two parallel mirrors which form its cavity. One of the mirror will be 100% reflective, and we also make it slightly concave. As you know, that makes the adds stability to the cavity. That makes the cavity more stable. And there will be an output mirror, which of course is a partially transparent mirror, through which a part of the light that is being that actually builds up inside the cavity can be coupled out. The useful loss which will make the laser beam. So now, first and foremost, you have to couple. Now, this is our pump laser, which gives a directed beam of light. This has to be coupled into this cavity, into this laser beam. Before moving further, let us now spend a little time on the energy levels which are involved in the lasing of this gas laser. Let us assume that it actually based on a simple 4-level energy scheme. So you have the ground or the source level, ground level or the source level. Initially, all the atoms or molecule, most of them reside in this level. So in order to create population inversion, these molecules have to be transferred to the upper level. But as we know that in a 4-level scheme, it is an upper level is not directly pumped. Actually, you use another energy level which is located slightly above this upper level, which is called the pump level. So this laser photon should be able to excite this molecule from the ground level to this pump. Let us assume that this wavelength is lambda 1. So this laser emits photons of wavelength lambda 1. Of course, it has a spread, but the spread is very narrow and it lies, and the frequency, most of the frequencies emitted by the laser lies within the absorption broadened feature of this gaseous medium. Now, once these atoms or molecules are pumped to the pump level, they quickly relax to the upper laser level. And suppose this is the lower laser level, and the lasing transition between upper and lower laser level emits light at a wavelength lambda 2. Surely, lambda 2 is more than lambda 1 because this energy is more than this energy. So basically, in this system, the pump laser should operate wavelength lambda 1 and it will pump it, and this laser will lays at a wavelength which is lambda 2. So essentially, you are converting coherent light of wavelength lambda 1 into another coherent light of wavelength lambda 2. But how do you couple this into the medium? You would, of course, need a mirror which will reflect this, lambda 1 into the gaseous medium. And as this photons travels through this medium, it will transfer the atoms or molecules from the ground state to the pump level, and eventually population inversion will be created. And stimulated emission would begin, and amplification of light will start at a wavelength lambda 2. Of course, it will be seeded by the photons emitted by spontaneous emission. The photons which travel along this will trigger the stimulated emission. Now, this wavelength, so this mirror should reflect the wavelength lambda 1, and when the oscillation begins, that is the lasing photon starts to build up, this mirror must allow transmission of this wavelength to, so that it can oscillate back and forth inside the cavity, and the photons light builds up at this wavelength inside. So this mirror then must reflect light at wavelength lambda 1, but transmit light at wavelength lambda 2. Now, an ordinary mirror, of course, will not do such a job, as we know very clearly. Even a conventional dielectric mirror also would not provide this feature. That is, it will reflect one wavelength and at the same time transmit another. Actually, a special kind of mirror called dichroic mirror works here, because dichroic mirror actually reflects one wavelength and transmits another wavelength. Now suppose you specially design a dichroic mirror in such a way that, say, you have made a dichroic mirror which, if you shine it with a beam of light that contains two wavelengths, lambda 1 and lambda 2, it will reflect lambda 1 and it will transmit. So such a dichroic mirror is going to work here. So what you do, you basically put this dichroic mirror. So then it will reflect lambda 1, and it will, and as the light builds up in this gaseous medium at wavelength lambda 2, it will actually transmit to this dichroic mirror because it transmits lambda 2. And therefore, it will allow to and fro oscillation of light at wavelength lambda 2. Therefore, the amplification of light at wavelength lambda 2 will be possible. Hence, this would raise eventually the output will be merged at wavelength lambda 2. So then, this way, a laser can be used, a pump laser can be used to pump a gaseous medium, a gas laser. Basically, it will convert the coherent light at lambda 1 to coherent light at another wavelength lambda 2. Of course, lambda 2 will be lambda. But there is a major disadvantage of such dichroic. You see, dichroic mirror is very expensive, and it has very low optical damage threshold. Low optical damage threshold. And so they are actually very easily they will get optically damaged if the optical intensity is very high. This is a special dielectric coating. The coating can easily be damaged with if the optical intensity, light intensity that it sees, if it is high. And the chance of its damage is actually greatly enhanced because inside the cavity, in a cavity, there is a cavity, the two counter-propagating waves, they interfere and form a stationary wave. So these are called nodal plane, nodal, and these are antinode. At the nodal plane, intensity of light is 0, as you can see, while at the antinodal plane it is maximum. Now here I have shown only few such nodal and antinodal planes, but in reality there will be innumerable number of nodal, because say for a conventional length, a cavity of conventional length, so 1 meter, the wavelength, if we consider visible light, which has wavelength say about 500 nanometer, so within 1 meter there will be 1 meter means 10 to the power 9 nanometer by 500 nanometer is the wavelength. So it will be 10 to the power 7 by 5. So 2 into 10 to the power 6. That means 2 million wavelengths can be accommodated inside this cavity. So you can imagine there will be so many nodal and antinodal planes that will fill the length between this output mirror and the length between the output mirror and the back mirror. Now this dichroic mirror, the location of the dichroic mirror can easily coincide with say, an antinodal plane where the intensity of light is maximum, and therefore it can be easily damaged. Already its damage threshold is low, and if it sees large optical power, optical intensity, large intensity of light, it can easily get damaged. So what would be the remedy? Remedy would be, of course, to try and use an optical element which has no such dielectric coating, which will have very high optical damage threshold. So it would not be damaged with such intracavity optical flux. So the technique would be to couple the light of that pump laser through a Brewster plate. So before I move any further, let me very quickly, you have already learned what is the property of Brewster angle. So let me very quickly refresh your memory on this property of Brewster angle. You see, let us do a very simple experiment. You take a glass plate and shine it with a beam of light emitted by a laser. You have a glass plate and you shine it with a beam of light emitted by a laser. As you know that this will reflect as you know it will reflect part of this light and another part will be transmitted. And let the angle of incidence of let be theta. We basically want to measure the reflectivity of this light as a function of this angle of incidence and also as a function of the polarization of this. So we want this beam to be obtained from a laser that can give polarized light. Now, let us assume that we would perform this experiment for two types of polarization. One is parallel polarization, which is called P. The other is orthogonal polarization, which is usually denoted by S. You know that. So the P polarization is the polarization which is contained in the plane of incidence. And plane of incidence is defined. Plane of incidence is the plane which contains the incident light and the normal to this element. So this is the normal, and this is the incident light. So the plane of this paper is the incident plane. So the polarization which lies in this plane is called P polarization. So first, the laser, let us assume, is giving a light which is P polarized. And you want to measure the reflection of this light as a function of wavelength. So if you plot it, if you would remember that it looks like this, for this is this P polarization and this is this polarization. So for F polarization, if you plot the reflection as a function of angle, so for P polarization at 0 degree angle, then that is for normal angle of incidence, it reduces, goes to 0, and then increases to 100% at grazing angle of incidence. So this angle is called Brewster angle, which is denoted as theta P. While for P, this is for P polarization. While if you do this experiment for S polarization, that means the polarization is perpendicular to this plane of paper. For that, the reflectivity continuously increases and eventually goes to 100%. So the P polarized light doesn't reflect at an angle of incidence which is called Brewster angle. So you take advantage of this and you actually couple your pump light into the cavity. How do you do that? Let me very quickly explain to you. You see, so you have the gaseous medium which you have to pump, and here you put your Brewster plate. That is glass plate, and this is your output mirror, which is a partially transparent mirror, and this is your 100% reflective concave, which this two forms the cavity of your pumped laser, which you will be pumping and operating. And your pumped laser here, and you actually align this in such a way, so this is at wavelength lambda 1. Your pumping wavelength is at lambda 1. And so this is Brewster theta. You align it in such a way that this light is incident on it at Brewster angle. And you choose the polarization of your laser in such a way that it needs this polarization. So at Brewster angle, S polarization, as you can see, S polarization at Brewster angle is partly reflected and rest will be transmitted. So a part of this light will be reflected and rest of it will be transmitted. So one part will be reflected, the other part will be transmitted, which will escape anyway. You don't worry about that. This escapes. But the part of this light which will be reflected, it will interact with this medium and will cause pumping. That means from the ground state, the atoms or molecule will be transferred to the pump level. And from there, they will quickly relax to the upper laser level. And then lasing will occur here, and it will generate light at wavelength lambda 2. Now, initially, this emission will the stimulated emission will be triggered by spontaneous emission, and spontaneous emission will occur at random polarization. So the light, that stimulated emission will be seeded by this random polarized light, which will be randomly polarized as a result of stimulated or spontaneous emission. So the stimulated emission in the beginning also will give rise to amplification that will be randomly polarized. So it will have both the polarization, that is that lambda 2 wavelength. Now, this wavelength, this polarization, perpendicular polarization, partly will be reflected and partly will be transmitted, while the parallel polarization will be entirely transmitted. So in every reflection, every round trip, part of the perpendicular polarization will be lost, and slowly, very rapidly, this intracavity light will be enriched in parallel polarization, and within no time, the amplification will take place only on people. Therefore, this will give out a beam of light at wavelength lambda 2, which will be on depolarization. So, as this is just an ordinary glass plate, it has no dielectric coating like the dichroic mirror, so its damage threshold will be very high, and therefore the possibility that it will get optically damaged is very less, and such a laser, such a configuration can be used for development of laser of quite high power. So I think I'll stop here. Today we have explained that how a second laser can be made to pump gas laser, which otherwise could not be pumped optically by conventional source.